seen this in our experience. If the air gets cooled down and if you keep cooling it, there will be a temperature below which the condensation starts to happen, right? I mean, here we don't have to cool the air in the entire room. We're just talking about some the small amounts of air that you're cooling locally in a small region. So the easiest way to cool the air is to bring it in contact with the cool surface. So you could bring, if you think about the cold water bottle that you take out from your fridge, or the cold can of Pepsi, Cola, whatever you take it out, you always see that small amount of water droplets start to form on the surface, right? Like the ones shown here, or like the ones shown in this picture. So these liquid droplets are what's called as dew, and this basically starts to happen once you reduce the temperature below the dew point temperature, or once you reduce the temperature after the air is already saturated. So basically, what we're saying is, if you keep cooling air, the relative humidity keeps on increasing till it reaches this point right here, where the saturation, the relative humidity is 100%, and the air is completely saturated because you're at the saturated vapor state. If you want to cool below that temperature, then the condensation happens. Now, the temperature up to which you can cool the air without condensation, or the temperature at which the condensation begins to occur, it's what's called as the dew point temperature. Okay, in really simple terms, it's nothing but the saturation temperature at the partial pressure of the vapor. Okay, at PV, that you already know of. So in this TV diagram that we have on the right, the point D is actually the dew point temperature. So if you keep cooling it till the point till you reach a temperature corresponding to temperature of state D, it'll still be in the vapor phase. But if you go below, for temperatures below temperature corresponding to TD, right, the condensation will start to occur. And this temperature corresponding to TD is what's called as the dew point temperature, or TDP. Okay. Now, what happens to the liquid that forms? What effect does it have on the let's say the vapor pressure, and how do we calculate how much of it has gone? How much of it has converted to liquid? So these are the questions that we want to ask and try to quantify them. Okay, and quantifying that is pretty straightforward if you understand what is happening in this process. So again, as we said, you have if you cool down the air below its dew point temperature, and here when I say air, I'm talking about the moist air, right? Dry air plus water vapor. When you cool it down below its dew point temperature, we know that some of the water vapor is going to condense, right? It's going to form liquid droplets. It's not in vapor phase anymore. It has converted to liquid. Okay. Of course, majority of it still remains as a vapor. So you starting from point 1, cooling it, and you reach point D. At point D, it is still all vapor. But if you cool it below point D, which is the dew point temperature, then condensation starts to happen, and basically at any temperature below dew point temperature, the amount of vapor within the air starts to reduce because the water vapor is turning to liquid. Okay, so the mass of water vapor within the air starts to reduce. The pressure, the partial pressure of the water vapor also starts to reduce. All right, now it'll continue along the saturation line though. Okay, it'll remain saturated, and although the amount of although the pressure of the vapor, or the mass of the vapor, keeps on reducing. So ultimately, when you reach the final state, right? Let's say this is state 2 is the final state here. The amount of water vapor in the moist air has reduced. Okay, the water vapor that initially existed in state 1, some of it still remains in the vapor phase, and it's shown by the partial pressure Pg2, whereas the rest has converted to liquid, and it's going to show up as saturated liquid at the same temperature, at the final temperature that you are measuring. Now, since some part of the vapor has converted to liquid, the mass of water vapor is less than the mass that initially existed, and therefore the partial pressure as well, Pg2, which corresponds to the partial pressure at the final state, is going to be less than the partial pressure at this beginning. And the simple reason why it is less is because we have been able to convert, or we have cooling at below the dew point temperature has converted some vapor to liquid. Okay, so it is not a vapor anymore, and we're looking at a gas vapor mixtures. So it does not come into the calculation anymore. Okay, so that's the whole point that we're talking about here. Now the key point is, we said, okay, some amount of vapor has converted to liquid. The question is how much of it has converted, and is there a way to find out? Well, the answer to both of those questions is yes. We can find out. So the amount of water vapor that condenses, if we say if we call it MW, is simply equal to the difference in the vapor content initially at state 1 minus the vapor content at state 2. So it's simply equal to the mass of vapor at state 1 minus mass of vapor at state 2. All right. If there's no difference between these two states, then absolutely no condensation has occurred. And as long as temperature is greater than temperature of dew point, the mass of water vapor at state 1 is going to be equal to the mass of water vapor at final state, whatever it is, as long as temperature is greater. Once you go at a temperature below the dew point, that's when condensation starts to happen. That is when the mass of water vapor at the final state, let's call it state 2, is going to be less than mass of water vapor at state 1. That's when the difference is going to occur, and this difference is basically what forms the liquid water. Now, how do we actually calculate this? So we said the mass of water vapor is simply equal to the difference in the masses of water vapors. We can write the mass of water vapor in terms of the humidity ratio and the mass of dry air, simply because the mass of dry air is the quantity which remains constant. Okay, and humidity ratio is something that's very commonly used to define the state of given moist air. Okay, so omega is the humidity ratio, and if you have forgotten, omega is simply the ratio of mass of water vapor divided by the mass of dry air. Okay, mv by ma. Now we can sort of divide this entire quantity, the mass of water vapor mass of water that got condensed, we can divide it by the mass of dry air to write it in terms of omegas, right? In terms of the humidity ratio for the two states, right? So we can write mw by ma as omega 1 minus omega 2. Why is it omega 1? Well, omega is simply mw by ma, and we are dividing this quantity on the right by ma. Okay, so here this is how you simply can determine the quantity of water vapor that's condensed per unit of mass of dry air. Okay, so simply subtract the humidity ratios for the two cases. Now, how do we determine omega 1? Well, it's pretty straightforward. Omega 1 is given by this formula, where PV1 refers to the partial pressure of water vapor at state 1, okay, at the initial state. Okay, and this is the mixture pressure. Mixture pressure is typically 1 atmosphere for almost all the cases that we consider. Now, when the cooling is occurring, there's nothing happening to the mixture pressure. All right, the only thing that's happening is there's going to be a readjustment of the partial pressures of the two components. What are the two components in the mixture? The dry air and PV. The sum is gonna remain as 1 atmosphere. It's not gonna change at all. So as PV reduces, the partial pressure of dry air will increase, simply because it's occupying more space now. Okay, so that's how you get omega 1. What about omega 2? Well, omega 2 is if you go back at the previous figure, state 2 was basically saturated vapors. So here, when we're looking at the partial pressures, we're looking at PG2, right? Or we're looking at saturation pressure at T2. So we just get PG2, that's the partial pressure of water vapor at the final state, and divide by P minus PG2. Again, the whole point is that omega 1 is going to be greater than omega 2. Okay, if condensation does occur. If condensation is not occurring, then omega 1 is going to be equal to omega 2. Okay, so this is how we determine the condensation, and as of now, just make sure that you understand how this is happening. We will talk more about how this condensation or the amount of water that gets condensed is useful for us. We're going to look at several applications where we make use of the humidity or the moisture content in air and play around with it to help us achieve our objectives, whether that's to achieve cooling or whether that's to condition the air to a state where it's more it brings it maintains the comfort level for us. All right, before we move forward, any questions up to this point? All right, everything is clear. Okay, so now let's talk about some more definitions. We're going to talk about few more definitions even after the adiabatic saturation temperature. So let's first look at adiabatic saturation temperature and why do we actually need this temperature? Why do we need to define it? Now, as we were discussing in the slide before, we mentioned that you know to get an idea about the moisture content of the air or moisture content of moist air, humidity ratio is an important factor. Now, apart from this, the other thing that is very commonly mentioned is the relative humidity. Okay, so these are the two things that give us an idea about the amount of moisture was in the air, right? Whether it's more, it's less, and how does it compare with the maximum the air can hold, and so on and so forth. Now, the thing is, it's not very easy to measure the moisture content. It's very easy to measure the temperature and pressure of air. Okay, that you can measure it with a simple thermometer and a barometer, but measuring the humidity may require some effort, right? So we define the adiabatic saturation temperature simply to explain the apparatus, which is an adiabatic saturator. So we make use of the adiabatic saturator to actually come up with the value for humidity ratio omega by simply measuring the temperature and pressure at inlet and exit of this device. Okay, so if you measure the temperature and pressure at the inlet and exit of an adiabatic saturator, you will be able to calculate the humidity ratio of the air entering the saturator. Okay, and that's all we care about. Okay, we want to find out what is the moisture content of air, and we want to do that by measuring some things which are rather easy to measure, and temperature and pressure are rather easy to measure. So let me explain to you what's happening here. You're sending in some air, some moist air, whose humidity you want to measure or whose moisture content you want to get, you want to calculate, right? Because you don't know it. And let's say we're sending it at a pressure P, temperature T, and with an omega, with the humidity ratio omega. Now this has a relative humidity less than 100%. So it means that it's not saturated, and it can take in some more water vapor. It has capacity to accept more water vapor. Now as you send in this air, you also have some amount of water here, right, which is slightly cooler, and this water is kept at TAS or the adiabatic saturation temperature. So basically you have cold water here at adiabatic saturation temperature, and you're sending in um, a, a moist air whose moisture content you want to determine. Okay, so this is state one. This is the air at this is the inlet state. Let me write it in so that it's easy for you to remember. And this is coming at a temperature which is greater than the adiabatic saturation temperature. So you need to basically select the adiabatic saturation temperature, or you need to select the temperature of the makeup water such that it is lower than the temperature of the incoming air whose humidity you want to measure. Okay. All right. So what's going to happen here? So this is cold water, and you have air which is unsaturated. So basically, if you keep this device long enough, the water starts to get evaporated. Okay, so the water will start to get evaporated and start increasing the amount of moisture content of the air. So if you keep this long enough, we can ensure that the air that comes at the exit of this device, it comes out in a saturated state, meaning at the exit its relative humidity would be 100%, and its relative humidity is 100% simply because it accepted a lot of moisture, right? It converted a lot of this liquid water to vapor. Okay, so let's say it comes out at pressure P, and it also gets cooled as it goes through this process, comes out at adiabatic saturation temperature TAS with the humidity ratio omega prime. Okay, now omega prime is greater than omega simply because we ensured that the air took in a lot of moisture, and because this thing is typically long enough, or the time of interaction between the moist air and the water is long enough, so it comes out at the temperature of the water and with slightly more humidity. Now, how does it all help? Well, we can simply apply energy balance to this entire device. Okay, so if you apply energy balance, you have the enthalpy of the moisture that's coming in plus the enthalpy of water, the two inlets into the system, would be equal to the enthalpy of the moist air that's exiting the system. Okay. Now, if you want to look at the TV diagram to see what the process is happening, we're starting with somewhere here, okay, T inlet at a temperature greater than the adiabatic saturation temperature, and then we are adding moisture. And as we add moisture, we are also increasing the partial pressure of water vapor. Okay, this is increasing. So ultimately, we move from this pressure line to a line of higher pressure simply because we have added more moisture. And we ensure that at the exit, the moisture comes out at the saturated state. So we are basically coming out at this stage. So this point corresponds to the exit state. Okay. So to make this simple here, to have a look at what's happening, we basically start from the inlet and then we keep on adding moisture and we follow this path basically to end up at a slightly higher pressure, what the vapor pressure for at a slightly higher vapor pressure simply because we have more moisture and at the saturated state. That's where we end up. So once you apply this energy balance, we can plug in these numbers here, and I don't want to go over the derivation as given in your textbook, but ultimately you end up with an equation for omega. All right. Now this is the omega, or the humidity ratio of the air that entered. So this is the humidity ratio of the incoming air, and this is exactly what we wanted to measure. And this is written in terms of the enthalpies of dry air, of vapor, of saturated vapor, and of saturated liquid. And if you want to measure, if you want to calculate these quantities, the only thing that you need here is the temperature. The temperature of the air at which the temperature at which the air enters the adiabatic saturation, and the temperature of the and the adiabatic saturation temperature, TAS. If you know these two, which are the temperatures at the inlet and exit of the adiabatic saturator, right? If you measure the temperature at the inlet and exit, you are able to calculate omega simply by making use of this formula. Okay. Same way, before I go and talk about relative humidity, let me also talk about this term right here, omega dash. Now, everything here depends only on the temperature, okay, in and exit temperature. Now, the omega prime is the humidity ratio at the exit of the system. And this is simply written in terms of the partial pressure of water vapor at the exit divided by the mixture pressure. So you can certainly measure the mixture pressure. It's more or less close to 1 atmospheric pressure. In most cases, it can be different as well, but it's going to be atmospheric pressure in most cases. And the partial pressure of water vapor at the exit again can simply be determined from the adiabatic saturation temperature, because we know that it comes out as saturated vapor. So PG is simply saturation pressure at adiabatic saturation temperature. So if we look at the entire device, we are measuring just the temperature and the pressure at the inlet and exit. Of course, there's no change in pressure between inlet and exit. The temperature goes down a bit. By measuring these two temperatures, we are able to calculate omega. Okay, so this is the whole point. And once you calculate omega, you can also calculate the relative humidity of the air. So the whole point of the adiabatic saturator is to basically to give us quantitative data on omega and phi without directly having a device to measure the humidity.